Hi, this is Dr. Viv. In this second part of the two-part video, I'll be solving the same system of linear equations that we saw in the previous video, but by a more formal technique. Now, this system is not exactly looking the same because of the last equation. Last time we had 4x plus 20z equals 12. This time I divided the whole thing by 4 to begin with, but the solutions will not change because dividing both sides by something the same thing will not change the solutions. This will make the computations in this method much simpler. Now the approach that I'm going to follow is called the cofactor approach. And it works like this. Suppose I can write this thing in matrix form. So I'll get 2, 5, 1, 1, 1, 2, 1, 0, 5 times xyz is equal to 2, 1, 3. Now this matrix way of writing it allows you to make this very compact. Last time I called this determinant A. This is sometimes called the coefficient matrix, and I called this coefficient matrix A last time. XYZ is sometimes just called capital X, and the right hand side of this is called the coefficient column vector K. So what I've done is I've simplified this equation to make it look like a much neater, more compact expression, and that expression is AX equals K. Now mathematicians love compaction. When things look this compact, it means that you can invent some techniques to get X all by itself. One of the techniques in matrix theory, and later on we'll see this is rooted in the group structure of matrices, is to multiply both the left side and the right side with what's called the inverse of A. If I did that, I'll get A inverse AX equals A inverse K. Now by the way, this inverse does not always exist, but it exists when the determinant is equal to not 0. It's some value other than 0. And last time we saw the determinant in the previous example was negative 24. So the determinant in this example is going to be negative 6 because I've already divided the third equation by 4. Because I know beforehand the determinant is not 0, I can be sure that this method will work. A inverse times A is just the identity matrix, or multiplying the whole thing by just the unit matrix. By the way, the unit matrix itself looks like this. It zeros everywhere except the diagonal, and the diagonal is all 1. This is sometimes called the unit matrix. So I'm getting the solution. X is A inverse K, and we have solved the problem. Now the big question is, what is A inverse? How will I find A inverse? So the formal definition of A inverse is the following. It is the transpose of the cofactor matrix divided by the determinant of A, and this is why it's important for the determinant to not be 0. Now what is the transpose? Let's first study what the transpose is. Transpose is easy to write. A transpose would be the same as A, but with rows and columns interchanged. So rows become columns and columns become rows. But it's not A that we're taking the transpose of. It's this cofactor matrix, A cofactor. So what is that next? To explain what the cofactor is, let me do this by a simple example, it might be more appropriate to talk about a cofactor in terms of a simple example. You have to first form what's called a minor. So if the matrix A can be written as a bunch of elements, and the most general element is Aij with ith row and jth column, so that's the ith row and jth column element, then the matrix alpha ij will be the determinant. The quantity alpha ij is a determinant of a new matrix with the same rows and columns as the original matrix, except an entire row and an entire column which was controlled by Aij omitted. So this is a matrix of one dimension lower. If this was an n by n matrix, this would be an n minus 1 by n minus 1 matrix. So whatever alpha ij controlled this way and this way are killed when you form whatever Aij controls will be killed when you form alpha ij. And that's the determinant of whatever you get here. Once you form the alpha ij's, the cofactor matrix is just the assembly of all these alpha ij's with a proper sign factor. So if I want to write the cofactor matrix Cij, the Cijth element of the cofactor matrix will be negative 1 to the power I plus j of these alpha ij's. And then once you form the matrix, the cofactor matrix, that will be called A with the tilde. And then you take the transpose of that cofactor matrix. And then you divide by the determinant. So it's a very long and laborious process, and this is most suited for just computers. So let's try this for the same example. So I have to formally create this cofactor matrix. So the determinant, I've already told you what it is. Let me just quickly run through the calculation of the determinant first of A. Now once you've done this many times, you don't really need to write anything down. It's 2 times plus 2 times 5 minus 0 minus 5 times 5 minus 2 plus 1 times 0 minus 1. So that's 10 minus 15 minus 1, which is minus 6. And that makes sense because that's minus 24 divided by 4, since the final equation has been divided by 4. So that's the easy part. The cofactor matrix next. So that's A tilde. I'll leave a lot of space here. It's going to be a big object, because each element of the cofactor matrix is going to be a determinant, alpha ij. Fortunately, since A is 3 by 3, alpha ij is just going to be 2 by 2. So the first cofactor is a cofactor of 2. What's a cofactor of 2? This is killed, this is killed. Remember, whatever this controls is killed. What's left over is just this part. And that comes with a plus sign. The signs I'll write in a different color so you can understand the sign convention. The cofactor of 5, that gets killed, so 1, 1, 2, 5. Once you do this a couple times, it becomes really second nature to you, and there'll be plenty of practice problems in the homework. The last method, the last cofactor on the first row is 1, 1, 1 0. Second row, that's minus 1 to the power second row plus and the first column, so it's minus 2 plus 1, which is minus. The cofactor of minus 1, well, this gets destroyed, this gets destroyed, is 5105. Then I get a plus, because that's minus 1 to the power 2 plus 2. This element is 2115. And then I have a minus. That gets killed, 2510. Last row, 1 gets 5112. There's a plus sign because it's the third row and the first column, so 3 plus 1 is 4, and minus to the 1 to the power 4 is plus 1. That's a minus. Here I get 2112. Again a plus, and 5 controls 2511. There, I've written out the cofactor matrix. That's a big job, and that's done. Next, this can be simplified. That's 5 minus 0, 5. And that's going to be 5 minus 2 or minus 3, 1, actually 0 minus 1, 25 with the minus sign outside, 10 minus 1, which is 9, and 0 minus 5, which is plus 5, because that's a minus 5 and there's a minus sign outside. Last row is 10 minus 1, 4 minus 1, but a minus sign outside. This is 2 minus 5, which is minus 3. Okay. Last order of business is to write what A inverse is. A inverse is the cofactor transpose divided by the determinant of A. Determinant of A is negative 6, so when I divide I get negative 1/6. The cofactor transpose, now this is the cofactor. I have to transpose it, which means I have to make the rows the columns, the columns the rows. So let me just take the rows, each row, and make it into a column. So I get 5 minus 3 minus 1, and 25, 9, 5, which is the second row, becomes the second column, and 9 minus 3 minus 3, which is the third row, becomes the third column. Okay, I don't think it's worth simplifying it because you're going to get ugly fractions if you do so. Let's just proceed to write the formal solution. The formal solution is x equals A inverse k. So that tells me that xyz, which is really what x stands for, is A inverse, which is negative 1/6 times all this here, times the coefficient vector k, which, remember, in this particular example it is 2, 1, 3. Now it's just a question of multiplying those things. So let's do this. 5 times 2 is 10. 25 times 1 and then 9 times 3. Next entry will be, so just as a warning, this is a 3 by 3 matrix, and that's a 3 by 1 matrix. So the result, if you cancel out these two 3's, is going to be a 3 by 1 matrix, or in other words, a column vector. Negative 3 times 2, 9 times 1, negative 3 times positive 3, and then I get negative 2, positive 5, and negative 9. We're almost there. So I get x, y, z is equal to, now let's do the math here. When I add these, I get 12, negative 6, because 9 and 9 cancel out, and then also negative 6. It's the exact same answer that we had before, and that's negative 2, 1, and 1. So x is negative 2, y and z each are 1. So it agrees with what we had before.